inviting me. Secondly, I would like to say that this is again, as Vijay had said, this is the first time that I am not talking about quantum matter in quantum matter conference, but nevertheless it is quantum technology. So this is very pulse scheme for coherent manipulations of electron spins in a ensemble of nitrogen vacancy centers in diamond, and some of the thing is published here, but actually mostly this is unpublished. We are still working on its ongoing work, and the graduate student is Anubhav Nandi. He is in the audience. He will be giving another talk at the end of this session. So I would very quickly, briefly introduce what is nitrogen vacancy center in diamond, and then the setup, which is how optical detection of magnetic resonance is done, pulsed ODMR and Rabi oscillations, spin echo measurements, and how the spin bath is coupling and actually spoiling things, and how to use dynamical decoupling to reduce the effects of environment. In this case, it could be spin bath. In other cases, it could be a phonon bath. And finally, dynamical decoupling as a filter function. So this is something electronics engineers do a lot, and we would talk quite a bit about it. And Anubhav is going to talk about filter function in a different sense in his talk. And finally, conclusions and future work. So the color is not coming very well. But so basically, this is the diamond unit cell, and we can actually substitute knock off some of the diamonds and put nitrogen there, and the adjacent, if we keep this vacancy adjacent, then this constitutes actually a spin 1 system. However, what happens is, because of crystal field splitting, so the spin 1 systems actually split into m is equal to 0, the multiplicity m is equal to 0 and m is equal to plus minus 1, and this is degenerate, and there is a gap of 2.87 gigahertz in the system. And how do we get ODMR, the optical detection of magnetic resonance, is that we come with a green laser, so which is 532 nanometers laser, and we excite the electronic spin from the ground state to the excited state, and it goes well beyond into the vibronic levels, and then it comes down non-radiatively, and if it goes from m is equal to 0, it will come back to m is equal to 0 and come down to m is equal to 0. If it goes from m is equal to plus minus 1, it will come down to plus minus 1, but from plus minus 1, when it comes down, it doesn't come directly to plus minus 1. There is another route, and it has a significant probability of going through a singlet state and then coming back to the singlet state. So what happens is, after a while, 80 to 90% of the spin 1 is cycled into the m is equal to 0 state, and that is in quantum computation parlance called the initialization of the qubits. But that is also a detection scheme, because this cannot be detected in this in the area of interest or the detection scheme that we are employing. So if it goes from m is equal to 0 and comes back to m is equal to 0, the detection probability is higher, so it is called the bright state. And if it goes from here and it comes back here, so through this, then I will not be able to see it. So basically that is called a dark state. Okay, so that's how we do the readout, and that's the final step of quantum information processing. Okay, so we have hyperfine levels and all, so that's not important. So this is the experimental setup. So basically we put a green laser here, and through we modulate this laser using a cost-optic modulator and put it in the sample, which is on a microstrip line, and it's actually so microstrip line is actually like a microwave antenna, and it's actually used to excite the microwave, so basically to pass the microwave there and to excite it, and the green light again goes back, so there is a dichroic mirror which stops the green light, and it only allows the red light, which you saw in the last slide, so which is basically the photoluminescence, and through this we detect in a avalanche photodiode, and from there we put it in the oscilloscope, and we basically, using this pulse blaster, we can actually pulse the microwaves, and and also drive the AOM. Right. So this is optically detected magnetoresonance. So basically we put the laser pulse, which is an initialization pulse, and then you come with a microwave. So the system is on resonance, in the sense we apply a DC field, magnetic field. So it has a resonance frequency, which is the Lamarck precision frequency, and we apply the microwave frequency exactly at that, and that is basically that 2.87 gigahertz which I mentioned, and I sweep the microwave, and exactly on resonance there will be a dip, because what is happening is, it is actually, so if you go back, so when I switch on the microwave, I'm shifting some of the m is equal to 0 to plus minus 1, and as I said, this is a dark state, so basically the detection will come down. So that's why there's a dip here. Okay, and this is the pulse scheme. I'll just give the pulse, this is the pulse data rather, I'll give the pulse scheme in the next slide. So here, pulse is any day better because it is able to resolve the inhomogeneities that may be there in the sample in the using in the field. So it is able to resolve these hyperfine lines, whereas here it's not able to resolve the hyperfine line. So basically this is a lot significantly more accurate detection scheme. This is the pulse ODMR scheme. I put the laser, and then Anubhav is going to talk more about it, and then I give a space and I give the microwave pulses, and then again I give a readout pulse, which is, and then I get the readout. So because it's an optical readout, right? So this is something where let's say I will come to what is Rabi oscillation. Supposing I'm actually giving a so this is a Bloch sphere, and any qubit is basically a rotation on Bloch sphere, and depending on how I am giving the microwave, I am giving along the x-axis or y-axis, so this will precise. And there's a video, so I'll just do it. So you can see that it is coming down. However, if there are error in the pulses, if this is an ensemble, there can be chemical inhomogeneities, and for various reasons it need not go to the same place. There can be error in the pulses, it can end up in another place on the Bloch sphere, and if I keep on giving pulses after pulses, so this will take me somewhere else. So this has to be corrected, and that's a significant part, significant portion of this talk. So this is Rabi oscillation sequence. So if I have the spin here, so basically I initialize the spin to 0 by applying this laser pulse, and then I give a microwave pulse, and then again I give a readout pulse. Okay, so that's where it goes back, and I go on giving these microwave pulses, okay, with varying duration. Okay, so I vary the pulse duration. The frequency is fixed on resonance. There can be, of course, errors in frequency. So from the setup, there can be errors in pulses. So these are the errors which can actually cause sort of decoherence. So I'll skip this. I'll give that. So this is a Rabi oscillation data. Okay, and in this data, if I so this is the So basically, as a function of time, it goes on reducing, and that's expected. So for an ideal system, it will just keep on going. So you see here, so the Rabi that we calculated here, the spin coherence time is 834 nanoseconds. So this is a plot of the Rabi frequency. So the frequency can be calculated from here. The frequency as a function of the root of microwave power, and it is linear, and that says that this is coming. That's one of the acid tests of saying that this is coming from Rabi oscillation, indeed, and nothing else. Okay, so further Rabi oscillation frequency domain measurement. If I take the Fourier transform of this, then I see this is my main. So this is, sorry, the resolution is not that good. So this is about 2.5 megahertz, and there's another one which is coming because of beating, because we also have the nuclear spins coming from the nitrogen 14 atoms. Okay, so this is where we are actually really coming into the system. There is something called spin echo pulses, and that is very common in NMR and ESR kind of experiments. So you have a microwave pulse which is a pi by 2 pulse. So that takes me from 0 to on the XY on the equatorial plane in the Bloch sphere, and then I let it dephase. So since it's an ensemble of spins, so different spins may have different Larmor precision. There may be slight difference, and they will go like that. Okay, and then I apply a pi pulse, and that is going to bring me back, and this is a time reversal operation. So it will spin back, and because all these individual red, green and blue spins will precess with the same frequency in the opposite direction, so they will reach this place in the same, given the same rephasing time at the same time, and that is the spin echo. and then I put a pi by 2 pulse. In normal NMR ESR, I could measure here itself, but here I have to put a pi by 2 pulse because I have to take it back to the Z axis in order to measure, because this is optical detection. Okay, that's one of the difference, right? Then, and as you give more time, so so what happens in Spinnaker is that this dephasing and rephasing time, so I keep on giving a series of pulses where I keep on increasing this. Okay, so from here to here, and if you see the envelope, so that's how it behaves. Now this is up to 20 microseconds. Now if I increase this further up to 600 microseconds, then you will see that there is a revival in this Spinnaker, and we figured out that this is because there is an additional, you could imagine that there is a Lamer precession if there are this nuclear spins, so there's carbon-13 isotope, so which has nuclear spins, and that is also precessing at its own Lamer precession frequency, and that gives a kind of an AC field. So the background, the DC field also has an AC field, and that modulates. Okay, and this is that modulation. Okay, so this is actually something which is killing my system. There is an additional spin bath which is coming from the nuclear spins of the carbon-13, and that is actually destroying my coherence, spin coherence time. So how do I improve that? So that is the part of this talk, like how to design a set of pulses to improve my T2. Okay, so right. So there is a scheme called dynamical decoupling scheme, and that has been done like established very well in NMR, but we will do it in our system. So the scheme is as follows, like you put a laser pulse. Okay, so by the way, spin echo is also like a dynamical decoupling scheme. I'll talk about that later, but yeah, so I put the laser and then I put a pi by 2 x, so about x axis I put a pi by 2 pulse, then I let it evolve over time t tau by 2, and then I put a pulse pi, which is pi pulse, which is about the y axis, and then again I let it evolve over t by 2, and I put a pi by 2 pulse, takes me back to the z axis, and I measure. Okay, this is the readout pulse, right? So the only thing is I give, so let's say this thing, whole thing, I give n times. Okay, so this n times if I give, then this acts, so basically this increases my coherence times, and how it happens, so that it is captured is, this is like equivalent to high pass filter function in electronics. And how I'm going to say, so basically most of the noise is low frequency, and because it's a high pass filter, it is able to screen out most of the noise in my system. And now the rest of the talk I'll talk about, so let me just show the data first. So these are the, so this pulse is called, this pulse is called CPMG. Okay, the CPMG, Carr, Purcell, Maidgun and Gill. So yeah, Maidgun and Gill. So basically this is 2 pulse CPMG, then 8 pulse CPMG, then 32 pulse CPMG, and we have measured up to 1024. We are in the process of increasing this. So as you are seeing, the T2 is actually increasing. Okay, so the decoherence is happening here after this. So as I am going on increasing the number of pulses, I am actually increasing my coherence time T2. Okay, so this is a log scale, semi-log scale basically. This is log and this is semi-log plot. So what is happening? Why am I able to filter out the noise, the low frequency noise? So okay. So this is data which is effective T2 versus number of pulses. So effective T2, my spin relaxation time is actually increasing as I am increasing the number of pulses, and the coefficient is yeah. So basically, we got an effective T2 of milliseconds. Can you believe that? It's milliseconds, not even microseconds. Started from nanoseconds. So that's how I'm increasing my T2. Okay. So now, what makes this possible? Why is this working? Okay. How am I able to increase the T2 with this pulse sequence? So this is what is dynamical decoupling. So dynamical decoupling is basically a control. So this is a video I've taken from Wikipedia. So what happens is, let's say this. So I give a pi pulse, it comes here. Then I give a pi by 2 pulse. Okay, time reversal, and then I see the echo. That's what I have measured. So what happens here? So is that this rapidly, precisely time control pulses is refocusing by giving a time reversal, it is refocusing the system. So there are many pulses, CPMG, XY, UDD, okay, and we have done some of them. So I'm going to present some of these things here. So this is the principle. Basically, this is generated by our student, so undergrad students enjoy. So so that's what is happening. So I give a laser pulse, then I give a pi by 2 x time t by 2, tau by 2, then this would probably be y, yeah. So yeah, so then I give a pi by 2 x, and that's what I'm getting, the signal. Okay, so basically this creates a qubit superposition, then a pi pulse which refocuses the system, and again I give a pulse for taking it back to z axis. Okay, this goes back to z axis, and then I do the measurement. Okay, so this is my CPMG sequence. So I give the same thing. Okay, this I give like pi y, and then again pi by 2x. Okay, just see here. So this goes here like that, and then I give a pi y, right? So this, and then goes back, and then I give, yeah. Okay, so that's how the measurement is done, right? Now this is another sequence which is called XY4 pulse sequence. So in one cycle I measure this, and another cycle I reverse it. So so what is behind this? The physics behind this, so the maths or physics behind this, is that I have sufficient time to finish this. So let's say I have a Hamiltonian here. Okay, this is simple, the Zeeman term, and I add a beta t, which is basically the noise, a time dependent noise in the system, which I need to get rid of. So how do I do that? Okay, so if I write down the density matrix, the diagonal terms are the population, and the off diagonal terms are the coherence. That's the definition. So in the off diagonal element, I have this 0 to t, say beta t. Okay, this is the noise term. So this is going to cause the decoherence. Okay, so in an ensemble average, the coherence terms of the density matrix goes to 0, since beta t is a random field. Okay, so there is a theory paper where they have done this calculation of filter functions, so that I'm going to talk about. But let me first introduce what is a filter, why it works. Okay, so a very naive, from a very naive experimental list point of view. So I have an open quantum system, because the system, my qubit, is interacting with the environment or the bath. So H is Hs plus Hb. So this is a system Hamiltonian, bath Hamiltonian, and the interaction Hamiltonian. Okay. Now for pure dephasing, let's say HSB is beta by 2 sigma z. I had given such a term. So the phase, there is the accumulation of a phase which after time t is integral beta t dt. Okay. So random fluctuations reduce the off diagonal element of the density matrix, thereby destroying the coherence. Now the principle of dynamic decoherence suppress decoherence by applying the sequences of pi pulses, which I mentioned. We saw that in action in the videos, in the cartoons. So each pi pulse reverses the sign of the interaction Hamiltonian by sigma, because it's a time reversal operation. So it will reverse this, and instead of a continuous phase accumulation, the phase becomes like this, where your yt is plus minus 1. In one cycle it is giving plus pi, in another cycle minus pi, and it is cancelling the phase. So that's called the switching function. So the switching function yt is plus 1 from 0 to t by 2, and minus 1 from t by 2 to t. Okay, for a Hahn echo, which is the spin echo. Okay, so the pulse sequence therefore modulates the interaction between the qubit and the environment. Now I write down the Hamiltonian. This is a time dependent Hamiltonian, and remember that actually this is happening in the rotating frame, or rather the interaction picture. Okay, so HC is the externally applied control. Control is my sigma pulses that I am applying, the CPMG pulses, let's say. And this is the system environment interaction, which is basically for pure dephasing. This is beta by 2 sigma z, I have mentioned. So the control propagator, so if I have the time evolution, then this is basically a time ordered expansion of this. Now in the toggling frame, or rather the interaction picture or the rotating frame, so this would be so basically the Hn is going to be modulated in the following way. So a very simple example, sigma z is actually squeezed from both sides by sigma x, let's say. So for ideal pi pulse, the sign change sigma z goes to minus of sigma z. So the coherence function, so it's simply I put the yt here, okay, and using the interaction picture I can write down, so this is the tilde in the interaction picture, and the random phase becomes yt times bt. So the definition of the coherence of the qubit is therefore e to the power minus of I phi t. Remember that the off diagonal element had an integration e to the power minus of I beta t. So this is, which is interesting, which is a filter function formalism. Where does the filter function come from? So now express the environmental noise in the Fourier space, okay, and substitute in the accumulated phase here, where your yt, y of omega is yt e to the power minus, this is the Fourier transform of this. Now the quantity f omega, which is modulus of y omega square, is called the filter function, okay. So for the decoherence function, so assuming that it's a Gaussian stationary noise, I can write this as e to the power minus of chi t, where chi t is 1 by pi s of omega. S of omega is the noise power spectral function times the filter function d omega by omega square. If there is a question, I'll answer why this is 1 by omega square. So this is the filter function determined solely by the pulse sequence, the control thing. So this picture is taken from here. So imagine in the time domain there is this noise, environmental noise, and I am controlling my qubit like this. In the frequency domain or the Fourier domain, I will have it f of t times, so this is the transfer function, f of t times the power spectral density of the noise, system noise. So the coherence is defined as this, and the chi t is the transfer function is s times s omega power spectral density times the filter function, okay, by omega square. Right, this is the definition of the filter function. So right, so this suppresses order to a large degree, and the noise cancellation is achieved. So the dd as a filter function, dynamic decoupling, it can be written as -1 plus -1 to the power of this thing and this thing, okay. So and of course we get this transfer function, right. Next, I would skip this because this, so these people, so I did a very naive calculation, and these people derived it using a spin boson model, and very nicely I actually copied it from the paper, so this thing is not very good. So they basically model this system in the same way. So I remember that I wrote down this density matrix, and that's what they use, sorry, right. Let's forget it. So free induction decay, so basically this is again that same thing I mentioned, but that's in the rotating frame, okay, and this is the signal that they obtain. Let me just, so finally what happens is dynamical decoupling is a filter function problem basically, so this is the dynamical decoupling is a filter function. So this is your coherence function, that is basically your average of the sigma yt, this is e to the power minus of chi t, where chi t I had derived earlier. And the power spectral density is given by this is just the correlation function, the noise correlation function, autocorrelation, and then the filter function for the CPMG is given by this, okay. So now let me come back to my data, okay. As I am increasing n is the number of CPMG pulses. So this is the filter function so this simulation was done by the students. So this filter function, where n equal to 2, n equal to 4, so these act like a high pass filter, okay. So it allows, it's nearly 0, let's say it doesn't allow anything to pass here, this is actually off scale, and from here it allows. Most of the noise is actually low frequency noise, okay, environmental noise or spin bath and that kind of thing. So it will basically cut off anything which is below and only allow this. Remember that the transfer function is a product of the power spectral density times the filter function, okay. So the noise is there in the power spectral density. If the noise is cut off, then my system is not affected, okay. So this is another coupling. How much is that time? Just 1 minute. So this is another thing, which is the Uric dynamical decoupling, and Uric said, so what is different from CPMG is that here the pulses are given at, so previously it was all uniform, here the time at which it is given is not uniform and given by this, and because of that, so let me just get, so this is the data from UDD, okay, it's also similar, so I keep on increasing my n and there, but if you want to compare, so this is the CPMG and this is the filter and this is the UDD. You notice that at lower frequency this works better because So because it's faster, okay, and sorry, higher frequency it works better because higher the frequency it becomes faster. Here they have the same slope, but here it becomes faster. So this will work better if I have higher frequency components, okay, in the noise, right? So this is the power law, fit versus error bar, and this is a comparison between, this is the CPMG and this is the UDD. At higher number of pulses, actually UDD is going to take over. Okay, very good. So these are the references, and part of the power spectral density, etc., is explained very well in this, and Anubhav is going to talk about it. Okay, so let me acknowledge my students. So I would really like to thank my graduate student Anubhav Nandi and for the experiment, and there are several undergrad students, Srinjoy, Yashwardhan, Shayan, they all also worked, and project students also worked. And I would like to thank DST for funding. And yeah, this is the group. Thank you very much. Yeah.
Question?
It was mostly not quantum matter, so I don't know whether. Slide, which slide?
Time periodic thing. So I was expecting that you will show some signatures of time crystal or something.
No. So it's in the offing. Maybe next year I'll talk about time crystal. Okay. So it's not there yet. You have to wait. Yeah.
Any other question?
But this fellow, Ashok Ajay from University of California, Berkeley has done. It's possible to do. Yeah, it's possible. It's in the offing, as I said. We are thinking about it. Yeah. Let me first finish. This is actually not finished. We have XY pulses, XY4 pulses, XY8 pulses. So I didn't talk about it because of lack of time. But yeah, we are doing that. I'll write the manuscript and send you.
So
Yeah,
So
if you,
let's-
you can ask me later at the tea time any questions you have. Anubhav is going to also talk about some of the nuances. Okay, thank you very much. Yeah.
thank you, Dr. Krishna, for